Okay, we are going to start with students working a problem again. Students are getting plenty of practice working problems. And I roll the die, and it comes up 3. And 3 is, I know this is what you're hoping here. Hannah Armstrong, Eugene Carl, and Sarah Hull. We made it. Andrew was successful at gambling yet again.
I was. All right, I'll give you your $5.
Yeah, so that's your problem, superhero problem.
Yes. Sure, I can write it. 5 minutes.
So let's get into your solving please. Please try to explain to everyone what you're doing.
Yeah. I can write.
Well, it's true. What I mean,
So can somebody write the equation for me?
Okay, they're starting, so if you'll listen to them.
All right, so we're gonna start out with our that'll work. Equation.
53, is that it? Yeah, 53.
Oh,
Okay.
I see.
Okay. Gonna.
It's equal to mass times gravity, which is the 92 plus 53. So right now we're trying to find the force of the two people combined. So we're going to add the masses of the two people, which is 92 plus 53.
Oh yeah.
And then multiply that by the acceleration of gravity.
Negative.
Now, Sarah, based on our discussion yesterday,
It should be
you just did it.
Yeah.
You had a minus sign erased. Notice G is always a positive value. If there's a minus sign, it's going to be shown somewhere else. It's not in the abbreviation for G.
And then we know that if we do F equals ma, acceleration is 0 because they are they're not moving. And so we could do F net is equal to m times 0, which is, and F net is tension minus the weight. Sorry, I'm going too fast.
Which is mass times gravity.
Yeah. And so tension is equal to the number that we got earlier, which is 1,421 newtons. What's this number? That is 92 plus 50 newtons. 1,400 newtons. And so the tension that is on the rope is the same as the force of gravity of the two people, which is 1,421 newtons.
Is that a 4 or not?
That's a 4.
Yes. This is just for part B.
Part B.
Okay, so I did like the second mass M2 in this case. Okay, so then for part B, you take M2, which is just 53, and then you times that by gravity. So it's a positive 9.81. Because you're just wanting to find the tension for the second rope, or like the second part of the rope. That just equals 519. I mean, sorry, 0.4.
Wait, so let's see if so it doesn't matter. Nice. And so that's the tension that the second person applied in.
Any questions for them?
Yes.
So is that always going to be the case where those two are the same numbers?
That's because they're stationary, so they're not moving. So if they had a different acceleration, then that wouldn't be the case.
Okay.
But because, so if you did F net is equal to mass times acceleration, and acceleration is 0 because they're stationary, they're not moving. So then F net is tension minus weight. And so tension is equal to weight, so that's why you can do that.
Oh, okay.
I'm going to write that down.
You're done, right?
Yes.
Thank you. So that was a perfect solution. Now I'm going to go through a few steps that they didn't show explicitly, but that they did do to make sure that we're clear on the mechanisms here. So I've been talking, not for a long time, about free body diagrams, looking at the forces on an object. And so in this picture, we have two people. And we have to decide, what am I going to draw a free body diagram for? By the way, I see that DJ came prepared for this problem. What are we going to draw a free body diagram for? For part A, it asked me to find the tension in the rope above superhero. So I want to find the tension in this rope. And so to make my life easy, and this is exactly what the team did, I'm going to make my object for part A being both of the superheroes, well, the superhero and his sidekick together. And so for my free body diagram, I have here is superhero and sidekick. And then I look at what forces are acting on superhero and sidekick. And I have the two that they identified. The force of gravity for part A is what I meant by the FGA, is the combined mass of my object, the mass of the superhero plus the mass of the sidekick, times G. And then I have the tension A. And so then we have to decide what our directions are, and I, by convention, call the vertical direction Y. Have to write that down for it to make sense when I use an equation. And so then the sum of the forces in the y direction is equal to the mass of my system times the acceleration in the y direction, which, as was clearly described, 0. I look at the picture. Since tension A is parallel to my positive direction, right? I defined up as positive, so tension A is in that direction. It's positive. So I have tension A. And then I had force GA was in the opposite direction, so that's going to make it negative. Minus FGA equals 0. And that, I think, leads to Leslie's question. Is it always this way? Well, if the acceleration is 0, then we have the sum of the forces 0. And if there's only two forces on the object, it comes out easy. Tension A equals force GA which is exactly what Wes calculated. So I'm obviously not going to repeat his calculation. I'm just showing you the very methodical approach in a way that can keep you from making mistakes and make sure it's clear to you why you had to do these calculations, why the signs are what they were. So now if we go to part B, any questions about the method here for part A? None? Pretty clear? Okay, good. At least one person nodded her head, two people, then both women. Guys, you understanding? Okay, thanks, James. Now we go to part B. And part B, we have to make a decision. Find the tension in the rope between superhero and, I should have put TS for trusty sidekick. My mistake. So if I'm going to look for the tension between, that rope that's between the two is applying a force on both the superhero and the trusty sidekick. What direction is the rope putting a force on the trusty sidekick? There's only two conceivable answers. That's not it. The rope is pulling the trusty sidekick up, keeping him from falling down. What direction is that same rope putting on the superhero? The superhero is the upper one, right? Okay, just making sure. What direction is that rope putting the force on the superhero? Actually, that's one rope, isn't it? Okay, with it being one rope, there's actually a different answer. I'm going to talk about the big collapse of the, was it Crown Regency Hotel in Kansas City? Because it had what I thought was going on here, but then I just realized that's one rope. So in that case, life is easier. Life is easier. The rope was pulling up on superhero with the force we just calculate. So we just look at, for part B, the trusty sidekick. He's my object now. TS for trusty sidekick. Forces acting on him are, again, force of gravity, but now it's just the mass of the sidekick times G. Yes?
So how exactly did you know that when it's talking about in between, that it wouldn't be the superhero, that it'd be the sidekick or whatever?
Because the picture has the sidekick below the superhero.
So you just know that the one below, anytime you're talking about tension between them, it would be the person that's under? Like, that's what I'm wondering.
I didn't follow that?
Like, when you have two things like that are like hanging on a rope, anytime it's talking about the tension in between them, it'd have to be the person on the bottom?
Well, in this case, because there's only one rope, yes. Okay. If it had been two ropes, which is what I was thinking, like one rope is tied to the waist of the superhero and trust sidekicks hanging from that, then it would have been a different story.
Would it still have the same answer, though?
It would have the same answer, yes. The different story is that now the rope is pulling down on the superhero, whereas it's not if it's just one rope, which is the key to the bridge collapse that I'm going to talk about. So I have that, and my tension B is pulling up on the trusty sidekick. So once again, sum of the force in the y direction is equal to the mass times acceleration in the y direction, which, again, Sarah's explanation is 0. So looking at my picture, what should I now replace some of the forces in the y direction with? You have the Freebody diagram to make this step easy. Okay? Almost. Force of gravity is acting, but what direction is it acting? Downward. So since we had up was defined as positive direction over there, then force of gravity is in the downward direction. So I'm going to have minus the force of gravity B. And then what's the other force? Tension B. In what direction is that pointing? Up. Hence, the sign of it is positive. And now we can solve this for tension B is force gravity B, which once again is exactly what the team did. So they did all of the right work. I just wanted to make sure you see that methodology, why we do the Freebody diagram. Question back there, Michael.
So the part A, the gravity will be positive for which reason again? The 9.8 positive for?
The constant G is always positive. And the signs here came in by looking at the free body diagram and determining what direction that force is. Okay, so let's look at that, the problem that occurred with the collapse of the hotel. Now, it's a true story. You can look it up. I think it's Crown Regency Hotel, or maybe Crown Regency Hilton or something like that. It was a hotel in Kansas City that had a major catastrophe back in the early 70s. And what they had was some walkways that were hanging walkways. Here's the roof of the ballroom, and then coming down from that roof of the ballroom are some pieces of metal. And then they're, according to the architect's plans, there's a pin there, and those pins are holding a walkway in place. That's the design that was approved when an engineer designs a building, or an architect and engineer design a building. They have very strict safety protocols. They have to make sure the materials are strong enough to withstand much more than the anticipated loads on them. And this was considered safe. When they were having, I think it was a wedding or wedding reception in there, they had the very unfortunate situation of the whole thing falling down. And I think it killed over 100 people. Right? So we consider that a disaster. So anytime something like that happens, not just to point fingers, but to learn, there's a big investigation into what went wrong. And what they discovered was that the construction company came up with a genius plan to save themselves some money. And there's what the construction company did. Now, what's different between the two? It's a very simple visual difference. What's the difference they did? They have two separate supports on each side rather than one that goes all the way down. And so if you look at this, it looks like it's fundamentally the same. It's just it's two smaller pieces of metal. But what the construction guy didn't think about was in the original design, how much weight is supported by this pin. And of course, you don't have a number, but how many floors are supported by that pin? One floor, one walkway supported by that pin. In what was actually built, how many walkways are being supported by that pin? 2. That pin has to hold up twice as much weight. And the pin wasn't strong enough to hold twice as much weight. And so it was clearly the construction firm's responsibility here legally, and it serves as a lesson that we need to make sure when we look at these things, we look at our free body diagram, what forces are acting on that pin. You have the upward force. I should change color there. I thought I changed color. There we go. The upward force that is from the support thing pulling up on the pin. Then you have the downward force of the walkway, but that walkway is holding up all of this. And so when you do your free body diagram, you have to consider, so what is the walkway holding up all of that? And it's much bigger. Whereas in this picture here, the pin here just has one walkway pulling down and the support up. So we're not doing any numbers in this, but that's a very bad situation that occurred because the designers knew their physics, but the people who actually did the construction thought they found a shortcut. I'm kind of torn on what to do. I want to do a lot of problems. I want students to solve a problem, but I also need to insert a new idea today. And that new idea has to do with rotation. Now, we learned acceleration is the result of a change in velocity. And on the test, we had a question that asked what causes an acceleration in the car. And we had, speeding up, slowing down, and what was the third correct answer? Turning, changing direction. Changing direction because acceleration is change in velocity and direction is part of velocity. So what we're going to look at, the new material, is about the acceleration necessary to make something turn. So we first start with just a little understanding of rotational motion. We're going to come back to rotational motion much more in depth later. But right now I just have to give you an introduction on it so we can talk about this. So when things are spinning, if you're closer to the axis of rotation, so for instance, if this is spinning around in a circle, if you're closer to the axis of rotation, the distance that it moves in one complete rotation, the circumference is 2 pi times the radius. So if it's a small radius, the distance it moves is small. If it's a large radius, the distance it moves is much larger. But if it's a rigid object, the time it takes to do one rotation is going to be the same. So that means something on the outside has a much bigger distance in the same amount of time. What concept relates to distance traveled per time? Or is exactly equal to distance traveled per time? Okay, velocity or speed. Velocity has direction, speed doesn't. But the distance traveled per time, that is going to be different then, depending on where you are. But it's all rotating together. So we like to talk about the rotation by measuring how much angle it travels per unit time. Because for a rigid object, it'll have the same amount of angle per second regardless of where you are. And so we call the velocity or speed for rotation the Greek letter omega. That's the last letter of the Greek alphabet. It looks like a W, but it's not a W, it's an omega. And that's the change in angle. We use the Greek letter theta for angle divided by change in time. And so the angular speed is equal to the change in angle over change in time, or the angular velocity if you include direction. We're not going to include direction for now, but I'll just tell you. To get the direction for this, you use your right hand. You wrap your fingers the direction that it rotates, and your thumb gives you the direction of the angular velocity. So the angular velocity for this CD is coming out of the screen. You think about that and you get a little confused. But if you were to try anything else, a piece here is moving that direction, a piece here is moving that direction. The directions are different as it's going around the circle. The only thing that's consistent is the normal direction, the direction that's perpendicular to the velocity of every piece. And there are two normal directions, the one coming out and the one coming in. We use our right hand to determine which one we assign it to, and thus we call it right hand system. Some rules here for geometry. I think I talked about 360 degrees because the sun takes about 360 days to orbit the Earth, right? Wrong. What's wrong about that statement? The Earth is orbiting the sun, not the sun orbiting the Earth. But as viewed from the Earth, the sun appeared to move about 1/360th of the way around per day. And so ancients decided 360 was really powerful, and it must be we'll divide our circle into 360 pieces with the distance we see the sun appearing to move each day being a degree. That's a man-made unit, if you will. There is a natural God-made unit for angle. And it has no unit at all. We use the term radian so we know, oh, we're talking about the natural unit for angle. And so we actually can define an angle based on the ratio of arc length. So in this picture here, going from A to B is an arc length of delta S, and the radius. So the angle is equal to arc length over radius. If you do a complete circle, the circumference is 2 pi times the radius. You've all memorized that since you were young ones. And so that means that the angle for a complete circle must be 2 pi. It's unitless, but we say 2 pi radians so people know, oh yes, you're talking about the natural unit, not a contrived man-made unit. So we can translate between angle and distance. Now, I just said that the angular speed is the change in angle over change in time. But the change in angle, according to this, is change in arc length over radius. But change in arc length, that's distance covered per time, and distance covered per time we call the speed. And so just based on the definitions, the angular speed is equal to the tangential speed. Tangential speed is the speed in the direction of motion divided by the radius. So there's a simple relationship between the tangential speed and the angular velocity. If radius is bigger, if you saw that for V, if radius is bigger, you get a bigger tangential speed. If radius is smaller, you get a smaller tangential speed. Talking about units again. Since the natural unit for angle is radian, what should the natural unit be for angular speed? Radians per second, because we're taking angle divided by time. Radians per second. And yeah, we have kinematic equations for rotational motion that are exactly the same as they are for linear motion. There's one more variable here that I haven't talked about. I will write it down right now. Alpha is the symbol we use for angular acceleration. And that's the change in angular speed over change in time. And so using alpha, omega, and theta, along with time, we can build kinematic equations that are identical to the ones you've already learned, except for you replace alphas and A's, omegas and V's, and thetas. That's supposed to be a theta. I can't do it because of where it is on the screen. And X's. Okay, I'm going to give up on trying to modify it. So our kinematic equations then, we have omega is equal to omega 0 plus alpha t. Theta is equal to theta initial plus omega 0 t plus 1/2 alpha t squared. And that's the last of the three common ones. So if you could do kinematic equations with regular motion, you can now do it with rotational motion, all the same equations. Why is that important? I'm going to go right past here and right past here to talk about centripetal acceleration. A lot of people have heard the word centripetal, and most people probably have heard somewhere along the lines that there's no such thing as centrifugal force. How many people have heard that? Okay, not as many as I thought. In physics, we call centrifugal force a fictitious force. Fictitious meaning it doesn't exist. Now, a lot of people will say, but ever since I was a kid, I have experienced this centrifugal force. You can't tell me it doesn't work. I was in the car, Dad made a left-hand turn, and I slid over to the right and crushed my sister. And it wasn't my fault. I was pushed into her. Now, I don't know if you're anything like me, I helped a lot. But it felt like I was being pushed into her. Everyone have this experience? A lot of people say, see, centrifugal force pushed me into her. But that's not correct. If we go back to Newton's laws say that an object will stay in constant motion unless acted on by an unbalanced force. What does constant motion mean? Constant velocity, no acceleration. So if you're in that car and the car turns, you were going like this, you should keep going that direction unless a force acts on you to change your motion. So if you had a seat that had no friction between it and you, and the car turns, what are you going to do? You're going to slide across that seat so you can keep going straight until you hit the wall of the car. And then the wall of the car is going to put a force on you, pushing you so you make the turn. And so that force pushing on you to make you do the turn is what we call the centripetal force. So you're not being pushed into the wall, you're just trying to keep going straight. But the wall is pushing you to make you deviate from going straight. So it was simply inertia that was you trying to go straight, and then a centripetal force, a force acted on you, pushing you in to make you go around in a circle. You had a question?
I don't think it's a number or anything, but what is that other thing? Centripetal, whatever the...
Okay, there's centripetal and centrifugal.
Yeah, what is that? That first one.
The
second one, sorry.
Okay, well, I'll say them both. Centripetal means toward the center. And that's real. When you're in the car and it goes around a corner, you are pushed toward the center so that you can't go straight. Centrifugal, that's spelled with an F. Centrifugal is the way I say it because I'm crazy that way. Is away from the center. And that's fictitious. There's no force pushing you away from the center. You just have inertia trying to go straight. So now some calculus ensues. These pictures are trying to avoid having to do the calculus. And what you end up with is the equation at the top of the screen. If you're going to go in a circle, the acceleration necessary to go in a circle is the speed squared divided by the radius of the turn. Or the angular speed squared times the radius of the turn. So this here is called the centripetal acceleration. So if something's going in a circular path, it must have that acceleration. Centrifuges. This thing down at the bottom is supposed to be a centrifuge as far as I can tell. You have objects in there that are being swung around. Do you guys use centrifuges like in organic chemistry? What do you use it for? Separation. You put something in there, you spin it up, it spins really fast, and what happens is the stuff in there has inertia. That is, it has mass, because mass is a measurement of inertia. The stuff that's more dense has more inertia per little piece, and so more inertia means it wants to go in a straight line more. It's going to take more force to make it deviate. Things with less inertia, it takes less force to make them deviate. So what happens is things with more inertia get pushed to the outside, things with less inertia inside. And so you separate actually by density. Things that are more dense are in the outside, things that are less dense in the inside. So this principle is being used in the centrifuge. Now let's do a problem, me doing the problem. A problem that uses this idea in force problems. So here I have a roller coaster. And one of the things you should note is the radius is the shortest at the top. The radius starts, of course, with an infinite radius. A straight track has an infinite radius because you can think of that as a circle with an infinite radius. And then you start going to shorter radius, it's shortest at the top. Why do you have a shorter radius at the top than on the sides? Anyone thought about that? Well, we'll work through to get an idea. Let's say that you are in a cart that's going around this roller coaster, and notice it says, what is the speed of the roller coaster in meters per second at the top with this radius of curvature? And we want a downward acceleration of 1.6 Gs. What would, if it was, well, if you were in free fall, what would your acceleration be? It'd be what? Okay, 9.8 meters per second squared, or 1 G. That G means 9.8 meters per second squared. So you'd normally have an acceleration of 9.8 meters per second squared. Here it says at the top, you're accelerating downward at a higher rate than that. What that means is there's something pushing you down because acceleration is the net force divided by mass. There's something pushing you down at the top that's bigger than just your weight. If there's something pushing you down at the top that's bigger than just your weight, what must it be? And I'll clarify why that's not the answer later, because that's a very common answer. Well, let's look at a free body diagram of the person in a roller coaster car. So you're up at the top. Here's the car. Here you are with your hands up because you're that kind of person. Of course, you're that kind of person. So you have the forces acting on you are, I tried to change the pin color. Force of gravity equals your mass times G. What else could possibly be pushing down on you? Let's try it right now. What's pushing up on you right now? The force normal, in this case from your chair. When you're in that roller coaster cart, you're up, down, you're upside down. Your chair is putting a force normal on you that's pushing you down. Those are the forces acting on you in the vertical direction. We're going to pretend right now there's no horizontal force. So now I'm going to do some of the forces, and I'm going to choose a direction that makes sense. I want to choose the direction of my acceleration. What direction is my acceleration? At the top, it is down. It says right there, downward. So some of the force is downward. Now, when we're doing problems involving going in a circle, we use the term toward the center of the circle, the centripetal. So the sum of the forces toward the center is equal to the mass times the acceleration toward the center. Now, DJ had answered centripetal force. The centripetal force is never, ever a force acting on an object. Now, if I just say that, you can say, okay, so it was wrong, but that gives me no reason why it was wrong, just he said it never, ever is. The centripetal force is defined as what I just wrote. So you can either say the sum of the forces toward the center or the mass times the centripetal acceleration. Either way, I'm fine. That's the centripetal force. But notice it was the sum of the forces toward the center. It wasn't a force. It was just adding up all that are present. So in my picture, I take this and I say, okay, toward the center, both forces are toward the center. So if I add up the forces toward the center, since they're both toward the center, they're both going to be positive. And so the sum of the forces toward the center is the force normal plus the force of gravity is MAC. So now if I say, what's the centripetal force, I'm tending to say mass times acceleration toward the center. Force normal is not the centripetal force. Force gravity is not the centripetal force. It's the sum of force normal and force gravity here that's going to give me the centripetal force. Now, the problem asks me what the speed of the roller coaster is. I need to solve this for speed. There's got to be a part B here that I skipped out on. That's what's the normal force, I think. Oh, actually, we don't have the mass, so you can't ask that either. How do I find what the speed is? It actually is very simple and doesn't require any of the work I've done. I know the acceleration centripetal is 1.6 g. But it's defined as v squared over r. So that means v is equal to the square root of 1.6 rg, which I've run out of space in this slide for, so I'll go up here. And technically it's plus or minus, but we don't care about the minus answer. Square root of 1.6 times the radius, which is 14 meters, times 9.80 meters per second squared. And I'll just quickly calculate that answer, maybe. And that's 14.8 meters per second. If the roller coaster goes faster than 14.8 meters per second, what's going to happen? Is it potentially disastrous? Okay, Emily shook her head no. I would go with Emily. It's not potentially disastrous. You go faster, that means you're going to have a bigger centripetal acceleration. The force of gravity is going to be the same, so the force normal is going to have to be bigger. So you're going to be pushed down harder. But right now, you're being pushed down at 0.6 Gs, because gravity is pushing you down with 1 G. So the other 0.6 are coming from the force normal. So you're lighter than normal right now. You speed up a little, you might get up to your normal weight, but you're upside down. You're being pushed up. It feels like you're being pushed up. Really, you're being pushed down with normal weight. So speed up, not a big deal, until you speed up way too much. Slowing down, what happens? What's the force normal going to do if you slow down? Get smaller. Well, the force normal can only get to 0. Once you get to 0, what happens? You're in free fall. You're no longer in the seat. Once the force normal gets to 0, you're falling away from it. So if it slows down too much, you fall out. These roller coasters, most were originally designed so that you didn't have to have the bar or the lapse restraint on. You would stay in your seat just by physics. But then they decided it's more fun to make them so you have these things where you would fall out without those restraints, so you have, corkscrew turns and that kind of thing where, yeah, you need those restraints. Without them, you do fall and die. Question, Emily.
So if there's people of different weight in the cart,
Mm-hmm.
are they experiencing a different speed?
Okay. The question that Emily asked is, if you have people different weights, are they experiencing different speed? They're all in the same car, so they're feeling the same, they're having the same speed. And thus they're going to have the same acceleration because mass wasn't involved in the acceleration.
Because I was thinking like the force normal is what?
The force normal will be different, yes.
Okay.
The force normal will be different because that's the acceleration times mass. So it's the same speed for safety for all masses. But you do have, if you're doing something where you're being held in by the restraint, well, then the mass matters. But if you're just being held in by, it's turning enough that force normal is pushing on you still, it shouldn't matter. This is the problem I had set out for you. We clearly don't have time to do this again. We're not giving away the bonus points the way I want to because we don't have time for anyone to do this. Just give everyone bonus points. It actually is a nice sounding idea. Speaking of nice sounding ideas, because this is where I was going to end having you do the problem, let's talk about grading the test. Okay, the last 3 problems, for the first time ever, I just graded the multiple choice. The research said that you'll get the same scores on average as you do if you grade it carefully. And my experience last year was, that the scores pretty much did match between the synthesis problems where I graded normally and the application where I did just multiple choice. But average doesn't mean it's the same for everybody. And so there were a number of people, for instance, that did half a problem right and didn't do the last part or things like that. And I can't go back and retroactively make rules and say, those who thought to write a very careful explanation, I'll give points, and those who said, well, I did the best I can, he's only grading on multiple choice, get the shaft. So I can't go back and change the way I'm going to grade, or I graded the last one, because then people who wrote minimal stuff would say, well, I would have written it if I known the count. But what I intend to do for the next exam, unless you guys object, and if you object, you got to let me know, is to have options. You can either take the multiple choice score for the last 3 problems, or you can have me grade all 3 problems in the traditional manner. And you can make the choice after the test. But I'm only going to grade what you wrote on the test. So, if that's something you're thinking of, you want to make sure you have it written in the right way. And I'll describe what I'm looking for when I grade it by hand in the future. I don't have time right now. But I want to try to have the fairest grades, the ones that show best what you understand. So a little mistake does not cause you to lose 10% or 13% on the exam. So I don't think that there's objections, but whenever there's a change in the syllabus, you have to bring it to the students. And if there's objections, I got to hear them rather than just make a one-sided decision. Yes, that's.
On the synthesis for your previous test, are those the ones that you gave the answer to and showing your work to get the answer?
Yes.
So on this test, are we going to get the answer again option?
No, because it will have one of the 4 or 5 answers will be the correct one. But no, I can't say, okay, I'm going to show you the answer and you either select the right answer or do the right work because, well, everybody would just select the right answer.
But so you're going to give us multiple choice still?
Yeah.
And we don't know which one's the right one.
Correct.
Yeah. You'll take into account like the work and stuff like that. Is that what you're saying? If
yes.
you decide
but if I do, I'll be taking in account the work for all 3 of the synthesis problems and throwing out.
and not just like
It won't be a Jeopardy situation. You won't be, okay, I want you to grade it by my work and then find out you get a lower score by the work. It will be the grader of the 2.
Okay.
Yeah.
So, how do I lose points on work?
Okay. It's time for class to be over. I'm going to answer this question, but if you need to go, just go ahead and leave. The points for the grading your work is broken down by, and I'll give you how many points for each, but drawing an appropriate figure to visualize the problem and help solve it, and then writing down the ideas that you're going to use to solve it, and then writing down the equations you're going to use to solve it, then putting your numbers in and doing the right math, and finally, 1 point for the right answer.
Wait, so then we have to literally write down the idea?
Yeah.
Like, this is what I'm gonna do?
Yes.
Okay.
Oh,
So students have the possibility to get extra credit for those who didn't do well on that really brought us down. Is there a possible way we can get extra credit to get our test grade up?
I don't see a good, equitable way to do that. I lean on the fact that we have drop tests to say that it's not going to overly penalize people, but it will require them to potentially take one more test than otherwise would have to. But I don't see a way to fairly do it in hindsight.
Like, this test is supposedly supposed to be the easiest one for us, the intro.
Well, it's the first one, not necessarily easy.
Oh my goodness, we destroyed
New
that.
material, regardless of, it would be easier if you were to come back to
It's such a
the hard, but
mess.
it's not easy at the
What
time.
about like curving the first one? There's a lot of
Some of them are high.
Yeah, there was 100% on it. And there are plenty of 97. Had question else?
No.
No.
I did type, but I didn't.
Would you be able to help me on a word problem?
Yes, yes, ma'am.
I've tried it 4 times and I don't want to try
Yeah,
it.
I don't want to try to.
Do you want me to go to your office?
Yes, yes.